they're losing profit, maybe they'll do something to
Yeah, but maybe so where I'll spend money is to trade money for time spent. So like in Hearthstone, you could play for a zillion hours and earn packs, or you could just drop $200 and buy just a ton of packs. So I'll do that just to save myself time. Same thing with Clash Royale. You know, I'll buy coins and diamond stuff so I can purchase the, you know, the chests to get my card collection bigger. Like, yeah, well, whatever, right? But at the end of the day, you still got to beat other people when you play. I mean, it's not like you got this. So, and then there's always the jump. So if you kind of boost yourself with having a bigger card collection than other people, then you can go up in the ranks pretty quickly until you hit your wall when you're up against the other people who have the same crap. Yeah. So it's just an expediter instead of a pay to win, because you do come up short even in Hearthstone. I probably spent, I don't know, at least $2,000 on Hearthstone. And I mean, I'm good and I'm competitive like in tournaments and stuff, but like not. I mean, the very best guys would consistently beat me. If I played them out of 5 games, I would probably win 1 game. So I'm capable of beating them, but not in any sort of consistent. And we're playing with the same cards. So at that point, it's just skill. You know, I could build the identical deck to what they have. They're just better at strategy and stuff, I guess. Huh? What strategy? in a video game. Not a what? Oh, no, I'm pretty good at spending money. Let's see. Oh, so I have a plug for a movie you should watch in a really weird, messed up way. It's on HBO streaming, but you can get it like on Amazon Prime for like renting it for $3 or something. The movie is called The Hunt. And it's hilariously fascinating. I want to say it's political satire, but it's wrapped in a movie about hunting humans. So the general premise is this. There's a group of people, and this all happens very early in the thing. Most of the thing is about hunting humans. That's why me and Mr. Gonzalez liked it so much. But the general premise is you have these elite people, these rich people who work for some big company, unnamed company. And they're on a group text message thing and complaining about first world problems or something. And one of the people makes in the moment a joke about like, oh, well, at least the hunt up at the manor is coming up soon, implying, you know, just making that statement. The hunt up at the manor is coming up soon. Well, so then one of these, which I guess was a joke, or at least not meaning what it ended up meaning. Well, one of those people, one of the elites, their account gets hacked. So this email address or the text message gets released to the public. Okay, so we'll call that group the elites, probably representative of the left-wing Democrats in the movie. So then the far right-wing Republicans get the information, you know, the folks that run these super you know, podcasts and things like that are, you know, all conspiracy theory. They get it and they create this whole story around it about, you know, how the elites are hunting humans, and, you know, they even say where it's at, some mansion in Vermont and all this stuff. Well, so the elites end up having to step down from their position. So they get ticked off. So they basically create a fantasy football draft to find the worst of the people that ultimately got them fired, and they make it real. they make it real. So then the movie is about the elites hunting the deplorables in this, and then hilarity kind of ensues. And the twist is, I won't tell you the twist, but I mean, this thing isn't winning any awards or anything, but from what's going on in the world today, and to laugh a little bit about something like, you know what, that could happen. Like, you take the people on the far sides of either side. Yeah, this could happen. I thought it was pretty. So Austin, did you see that particular movie?
Yeah, I watched that movie.
Okay. Yeah. So I mean, it's like weird, right? But it's like you're during the entire movie, even though they're hunting people, you're constantly making connections like, yeah, that's kind of like this one thing I saw on YouTube or something like that. I don't know.
It's almost just, it's like I kind of drew similarities to like if the Hunger Games was like more political. I don't know.
Yeah, I think there's truth to that. It
got banned for a second. The like release date was pushed back. There was a bunch
Really?
of like craziness.
Swanks in it? I mean, like legitimate, she hasn't been in movies in a while, but like a legitimate A-list actor, is in the movie. So it's. And if you like that movie, another one to watch that's been out for years, but it's not really political satire, would be Tropic Thunder. Tropic Thunder was great. When that movie first hit the theaters, nobody knew that Tom Cruise was in it. It wasn't part of any of the things. Just plays the crazy guy. That was probably Tom Cruise's greatest role in any movie. That was during his low point when you had all the Scientology stuff all over the TV. But he nailed that role. All right, let's do something important. Okay, so homework assignment was this entire thing, right? All right, but I verbally told you how to do merge. Is that what happened? Okay. So let's write this guy real quick. All right, what's it? Racket? Rocket, racket. Let's get rid of all that crap. All right, first one, flatten. Turns a list of the symbols contained in S list in the order in which they occur when S list is printed. Intuitively, flatten removes all the inner parentheses from its argument. Got it. Okay. So this second one here is probably a good example of what to look for. So we're calling flatten, and flatten knows how to remove a level of parentheses. So anytime we hit something that is a list, we need to call flatten on that list, right? So as we're going through this guy, we call flatten on this outer list. And what are we going to do? We are going to call flatten on this first part of the list. Now the kicker is this. This ultimately is going to come down to, we are constructing a list, right? We are the resulting output is a constructed list, but we do need to think about, so we have that same pattern. We're hopefully we're seeing that we have the same identical patterns popping up over and over and over again with little kind of twists. And one thing you're going to see later on is, even though these feel like little drill exercises, they're actually going to be very related to the interpreters we're going to be writing. So it's kind of a, it's like we're putting the medicine inside of the food. You're practicing this stuff, but you actually are doing some language theory stuff. Trust me. So we're going through this. We're going to say, I see a list as the car. So what am I going to do with that? Well, I'm going to have to call flatten on it. But ultimately, what is flatten going to return for me? It's going to return a list. If ultimately I want to produce a flat list like this, I don't want to cons my list onto the front of the thing I'm building. I'm gonna, what's the tool that we can use that takes two lists and effectively merges them together? Append. Appends are our magic tool for this one. So we will append the result of flatten on the car with the result of flatten on the cooter. But if the car is a symbol, not a list, then I would cons that symbol onto the rest. All right. So this kind of made us make that differentiation between append and cons. So we will define flatten could be a lambda that's going to take in a list of symbols as a parameter. And we'll go ahead and create our cond. Null list of symbols will return our empty list. So same pattern we've seen all along. List car list of symbols. If the first element on the list of symbols is a list, then what do I do with it? I'm going to append the result of calling flatten on the car of list of symbols onto the result of calling flatten on the cooter of list of symbols. Else, it must not be a list. So what am I going to do? I'm going to cons the car of list of symbols onto whatever flatten returns on the cooter of list of symbols. This one, empty list, list B. List. Did I not finish up? Else. Closed it in the wrong place. Ninja. So there's our list A, B, and C out of that guy. All right, questions about that one? So this one you should see the identical pattern we've been seeing all along, with our little twist being append versus a cons right then, in terms of what does the next step need to have. This was probably the difficult line right there. Because if you were trying to use cons, or you were trying to use lists to construct your list, you would have been stuck with a bunch of lists again inside of lists, and then you're like, well, why is it doing this? Okay. Next one is merge two lists of integers, both in blah, blah, blah order, merging them together. Okay, well, let's look at the picture here. All right, so merge is the second part of a merge sort, right? So we're taking in two lists of integers. Each of those lists we can assume is already sorted. So 1 and 4 is in order, 1, 2, 8 is in order. And what we want to do is we want to merge them together in such a way that we're left with a single list with those two merged together with the smallest numbers early and the larger numbers later on. All right, so we're going to have to be processing two different lists until they become empty. If they are both non-empty, then I'm asking the question, which car is smaller? And we're picking that guy as the winner. Make some sense? All right, so define merge to be a lambda that takes in a list of integer 1 and a list of integer 2. All right, we'll go ahead and do our cons. All right, so now we have several different conditions we're working with here. So one condition is we have an and null list of integer 1, null list of integer 2. And if that's the case, then we run out of stuff to merge. End with our empty list. All right, so if we get past that line, we know that at least one of our lists has stuff in it. They both might have stuff in it, but if at least one of them has stuff in it. So next guy here will be null list of integer 1. If list of integer 1 is empty, then I'm just going to pick my winner from list of integer 2. So I will cons the car of list of integer 2 onto the merge of list of integer 1 and the cooter of list of integer 2. So if list of integer 1 is empty, I'll just assume my winners from list of integer 2 and cons that guy on. And then I'm consing it onto the merge of my old empty list. List of integer 1 must be empty here. Started off empty, right? And the cooter of list of integer 2. Otherwise, if I'm looking at a null list of integer 2, then I'm going to cons the car of list of integer 1 onto the merge of the cooter of list of integer 1 and list of integer 2. So if the other guy is the one that's empty, then I'll pick my winner from the previous one. So these two lines here are just inverses of each other. One defaults the winner to list of integer 2. The other one defaults the winner to list of integer 2. Or 1 rather. Otherwise, we have a real race. All right. Both guys have something in the car. So now I want to ask the question, which one is the smaller? If less than car list of integer 1, then car list of integer 2. If car of list of integer 1 is less than list of integer 2, then I'm going to cons the car of list of integer 1, my winner, onto the merge of the cooter of list of integer 1 and the entirety of list of integer 2. If list of integer 1's first element is smaller than list of integer 2's first element, then I'm going to pick list of integer 1 as my winner. So I'll cons the car of that onto the merge of the rest of that guy along with the untouched version of list of integer 2. Else, the winner must be the other guy. So I'll cons the car of list of integer 2 onto the merge of list of integer 1 and the cooter of list of integer 2. One, 4, 1, 2, 8. So there is merge. Go ahead. What do you want to do? Yeah, these guys. I just returned the non-empty list. Oh, yeah. What he's saying is that we actually don't need to make another merge call. We know that from this point forward, the other guy is the winner, right? So we can actually cons this onto list of integer one. So we can replace, that does break our pattern that we've been used to doing, but you're absolutely right. We can take this guy right here and replace it with list of integer one. And we can take this guy right here and replace it with list of integer two. We don't actually need to make the merge call because from this point forward, we know we're just going to be feeding off of that list that has stuff in it. What's this? So here, let me undo this one down here. So when we call merge here, we're just feeding off of list of integer one. List of integer two, we know is the empty list. So from this point forward, calling merge on this effectively is wasting time because we know that each additional call, let's say that there's 50 things still inside of list of integer one. The next 50 calls to merge are just going to be grabbing the car of that list because the other list is already empty. So I already know since list of integer one is in order in and of itself, I can just take the rest of that list that's already in order and tack it on to the end of my current setup. Just like I did up here. If list of integer one is empty, so that guy is currently empty. Hold on, I do have this backwards. Cons. Yeah, I just need to return the list of integer two because this guy's already empty. So the real question is why did this? It only worked in this case because we only got to the point where it was the one list. It just happened to be the right setup. So really, it's just list of integer two, that entire list. If the other one's empty, my answer is this guy. Yeah.
But that list of integer one could be empty at some point during the rotation. That's not what we do.
True.
So wouldn't this set up at the end of it?
No, because this guy presumably is going to be as a result of consing, you know, the car of something onto the merge of this. So maybe this is where it becomes null. Then this guy right here would boil down to that list that maybe just is list of integer two. Then I'm consing this one value onto. I might still argue that from a pattern perspective, the way we had it written before the first time probably is the better practice for our pattern. This is an optimization of it, and not really a problem because we're going to have plenty of things that will end up being like this. So what he was just asking is to just return this list here, won't that become a problem because we've presumably already worked with some other things? What I have right here, let's say it's a list of 50 numbers that are already in order. That becomes the result of that guy right there. One recursive call that boils down to this list that got constructed somehow. It just happened to say, I'm not going to make any more recursive calls because here is your 50 numbers in order right here. That's all I had left. It's whatever's in list of integer one. Those are the only potential winners from this point forward. And my given information is list of integer one is already in order. All right, so that's probably relatively optimized. Any one of those is reasonable. Technically, our original one isn't the problem. We're just making a whole bunch of recursive calls when we could actually have predicted that we already actually have our answer because we're feeding off of a list that already is in order. All right, questions about that? So let's put that up on Slack. Oh, that's not it, right? Is it this one? All right, let's see what comes next. I just have the same slide twice. Oh, because I had you do the other one. Yeah, whatever. This was better for you. What's up? Well, this next one's going to be our merge sort. All right, so let's look at this one. So now, I mean, nothing says that we have to do a merge sort with this, but we already have merge written. So why not perform it as a merge sort? Okay, so what does merge sort say to do? Merge sort, let's go and look at this. So the 82523. I could probably steal this slide because we don't even know what this slide was all about. Let's just do this. Eight, 2, 5, 2, 3. All right, so let's look at merge sort here now. I'll give you the pre-warning that there's going to be a trick to this one. So we're about to look at traditional merge sort on this to remind us how merge sort works. But then when we go to implement this in Scheme, we might choose to implement it slightly differently than we have historically implemented it. I'll just give you that hint right now because I'm going to have you work on some of this here during class for a few minutes after I kind of push you in the right direction, but then we'll ultimately solve it. All right. So we have our list right here. We ask the question, is this a one list, right? For merge sort, we say, is this trivially sorted? This is not a one list. That means it's not trivially sorted. So what do we do with merge sort when it's not trivially sorted? Cut it in half. All right. So now, and I'll tell you this part right here, this is where the trick will come in when you go to implement this. I'll even zero you in on the trick. All right. But we're going to do this the way we've done this before. So are we going to have the big half, the first part or the second part? First part. Okay. So we'll go ahead and we'll split our list. So we have that list. And we have this list. Okay. But we've called merge sort merge sort on that left half first. And then we make our second call the merge sort on this right half. But this guy is not even going to happen yet. So he's just waiting to happen right now. So we've only made our first merge sort call. Is this the one list? Nope. Split it in half. Call merge sort on the first half. Is that the one list? Nope. Split it in half. Is that the one list? Yes. Is that the one list? Yes. So now what do we do to this list of integer? This is list of integer 1 and list of integer 2. We just wrote a function, right? We call merge. So we call merge. If we have a list that's partially sorted and another list that's partially sorted, and we want to merge those guys together, we already have we just wrote a function a couple minutes ago called merge that will do that, right? So that'll put these guys in order, which we will somehow get propagated back up here. Okay, so now this call to merge sort's done. So now we make our right hand call to this. Is this the one list? Yep. So now we have this partially sorted list and we have this partially sorted list. We call merge on that guy, giving us that guy, which somehow will get propagated. So now that's in order. Now we have our original second call to merge sort. Is this the one list? Nope. Call in the first half. Is this the one list? Yes. Is this the one list? Yes. Merge these guys together. They happen to already be in the right order. Merge these guys together. So we're left with two, 2, 3, 5, 8. And that's the result of our merge call on those two partially sorted lists. Make some sense? All right, so that's how merge sort works. So as a reminder for us. So now what we want to do is we want to implement merge sort. Back up to get my. I think this is the original, right? So now we want to look at how can we implement this in Scheme to accomplish what we just did. Ultimately, accomplish what we just did. So the challenging factor for us is we want to start thinking about, well, how do I split it in half? How do I find the middle? Now, we could write a bunch of helper functions, right? We could say, okay, I'm going to pass this list to a helper function, and that helper function is going to go ahead and it's going to give me maybe a list containing a list in a list, where the first list is the first half and the second list is the second half. And then we call merge sort. We append the result on merge sort on the first with the merge sort on the second and kind of just let it flow through that way. So the difficulty ends up being on our function that's meant to split this guy in half, giving us this list and giving us this list. That is difficult to do in Scheme. The way we handled that in Java or C++ or any other language was to do what? Keep track of the beginning and end of, keep track of the portion of the array, for example, that we were interested in. When we called merge sort on this guy, we were saying, I'm calling it on bucket 0 through bucket 2. I'm calling merge sort on bucket 3 to bucket 4. So we passed it the entire collection, but just kept track of which buckets we were interested in. Now, we probably could write something that sort of mimics that as well. But doesn't that sound like it's going to run us into some similar complexities to what we just talked about? Now you're having to say, okay, well, I no longer have to give myself a list of two lists, one being this guy and one being this guy. Instead, I'll just pass around this entire list with two integers, the 0 indexed position of my left portion and the 0 indexed position of my right portion. So I know which part of this list I'm dealing with. And then what I could do is I can write another function that goes up and says, okay, well, given this list and giving a beginning and end, give me the sub list that is the parts that I should actually care about. Again, writing helper functions to pull this off. All right, so I'm telling you, you don't need to do that. You don't need to write a helper function to make this, well, you might choose to write a helper function, but neither of those solutions I just gave you, which will work. All right, they'll be blood coming out of the ears and stuff like that, but it will work. You can make it happen. But neither of those are going to be the, let's call it the path of least resistance for writing this. Similarly, I'm not asking you to discover some built-in sort function, which I'm sure there is, you know. We're implementing a merge sort. All I'm telling you to do is get creative when it comes to splitting your list in half. Okay, I kind of understand the hints I'm giving you, the high level. But at the high level, I focused you in on where the situation is, right? Okay, I've said here's one solution. It'll work, but probably not the way you want to do it. Here's another solution. It'll work, but probably not the way you want to do it. Both of those solutions mimic what we just did, right? It's trying to make a list in Scheme behave kind of like an array in Java, where we're passing around the entire thing, but saying only focus on these parts. You can make that work. I'm telling you, you won't have to do that. Okay, there is a modification you can make to how you split the list in half that will make life easier. Go ahead. Sure. Yep. Half. Splitting it in half is a suggestion, right? Merge sort doesn't require them to be equal halves. We just saw one half was a three list, the other half was a 2 list. Oh, you know, somebody gets lucky every now and then. Yeah. Yeah. Do you? Well, that's going to run out at some point.
I'm not looking forward to that.
All right, so you know, we already saw that the 2 halves don't have to be equal. In our example here, we had a 3 list and we had a 2 list. So he's saying, well, does anything really prohibit us from having a 1 list and a 4 list? Not really. So if I did that, let's just bounce back up here. So if I say, is this the 1 list? Not the 1 list. The length of, and I've shown you the function for length of a list. I'm pretty sure I did, but if not, here. Length 1. Nailed it. The function called length. Pass it a list, it tells you how many things are in it. All right, how many elements are in the top level version of that list? And what I mean by that is if I say the length of 1, 2, 3 like that is only going to be 2. This list here has 2 elements in it. Element 1, element 2. This list has 2 elements in it as well. But a list is a collection of elements. This big list here has 2 elements. This is element 1. This is element 2. That whole thing. Make sense? So that's what length will give you, the number of elements in a list. All right. So we know how to ask the question length now. I think I'd shown that before, right? Okay. Well, it should be in the notes thing. You should be memorizing all the notes. You people think you need to sleep. It's just stupid. You memorize all the stuff, so later on you make the big bucks, then you can spend thousands of dollars on Hearthstone packs. It's the path to success. Exactly. You don't need sleep. You sleep when you're dead. But then you have all sorts of new places to explore. So it's, yeah, well, you never have to. Yeah, just don't waste your time. Let your body tell you when you need to sleep. You know, once you start going a little bit loopy, then you probably should sleep. If you're always loopy, well, that's just your baseline. You just have to adjust the baseline. Say, okay, well, you know, I'm a little bit south of north all the time. So this is normal. So I just have to operate off of this. All right. So we can ask ourselves, is the length of this guy 1? It's not. So I need to split it in half. So what am I going to do? I'm going to call merge sort on the first half, right? So now, is this guy the 1 list? Yes, it is. I'm done with that. Then we'll call merge sort on the second half. Super Ninja. Is this guy the 1 list? Nope. We'll call merge sort on the first half. That's the 1 list. We'll call merge sort on the second half. Is this the 1 list? Nope. Call merge sort on the first half. Call merge sort on the second half. Is this guy the 1 list? Nope. Call merge sort on the first half. Call merge sort on the second half. Call merge on those guys. Left with this. Call merge on these guys. We're left with 2, 3, 5. Call merge on these guys. Here, I need to. 2, 5. So call merge on those guys. Call merge on these guys. And we're left with our answer. So we simplified the way we split our list in half. Now, keep in mind that by doing this, we ended up with an accurate solution, but we did remove a lot of the efficiencies from merge sort. So merge sort, when we originally talked about it, we said that merge sort shines in a multi-process or even multi-computer type situation where you can divide the work in half over and over again and give little pieces of work to different things. In this case, we sometimes give half the work to somebody that's already done, right? So we give one of the CPUs a 1 list and say, hey, sort this. It's like, okay, back to Hearthstone. So I'm that guy, right? Then we give the 4 list to the other guy and say, get to work. And he gets, so whoever's on the left half sorting policy on any of these, he's the one who gets lucky in this algorithm. Everybody else is doing more of the heavy lifting. We're still dividing the work up, but we're not really splitting the work very evenly. So you could argue that we're actually probably giving up any efficiencies because of the amount of splitting we're doing anyways. It probably ends up being a break even, and maybe this guy ends up performing pretty similarly to a insertion sort or something like that. Probably not substantially better than that. All right, so questions about that guy? All right, so let me see where we're going here. All right, so your homework will be this guy here. This homework 5, writing sort and writing a second version of sort where we're sorting on a predicate rather than just necessarily less than. All right, so still the same, the same answer, the underlying algorithm. Just instead of saying, does this guy win versus this guy based on who's less than the other one, it might be we're sorting on greater than. For example, we can pass in the predicate that we're sorting on. And actually, even calling this a predicate is a little bit inaccurate because I've advertised predicates as being functions that take in a single parameter and return true or false, where in this case, we're assuming it's going to take in 2 parameters. The 2 things we're fighting over, and then how are we judging them? Okay, so predicate is probably a little bit of a weak word here based on how I've defined predicate. All right, so this will be your homework for what day is today? Tuesday. This will be homework for Thursday. Go ahead.
Just to make sure that I understand it,
You don't. Okay.
the First example in 1.30 is.
Yeah. Yep. Because the predicate we passed in was the less than predicate, which is the same as we assume is the default way of sorting up here when we're sorting in ascending order. This one says, well, what if we want to do it in descending order? We could pass a different predicate into this guy.
You don't want to put this
Reverse the list.
sorted in a whole.
Well, I don't necessarily care, I guess, but why would you, that would change the way you sort. If you're going to call your sort function. Yeah, I mean, you could do what you want, but I would say you would probably modify your merge, what we wrote in here, this guy, to not assume that. He would put the predicate in and say, who's the winner? So that's all that would change with merge. You probably have a merge pred, taking a predicate, and then just put predicate there. Make sense? All right, so we'll put that up as the homework. So let's keep cooking and start talking about variable environments. All right, so when we think about variables in a programming language, these are just name value pairs that we're storing somewhere, right? So, you know, when we first start talking about this in an intro programming class, we're trying to make that connection to how do human beings remember stuff. You know, we kind of say, well, what's your name? Somewhere in your head, in your, your human memory, you have a little variable called name, and next to it, you have the value that is whatever your name is. In a computer, we're going to assign a memory address somewhere to a variable name, and then at that memory address, we'll store a value, right? Well, when we're implementing this in Scheme, we're living at a one level of abstraction above that. We're not dealing directly with computer memory. Instead, we're going to have to build a construct that lives on top of computer memory that allows us to store collections of name value pairs. All right, so how could we store a single name value pair in Scheme, for example? Let's say I wanted to store a variable called name, and let's say age. I want to create a variable called age and set it equal to 21. How could I represent that in Scheme, knowing what you know now? Good. Okay, tell me more. We start with a list. What are you going to put in that list?
Whatever you're storing.
I said age equals 21. I'm just going to put, so I'm going to create a list here. Put a 21 in there. I've lost track of that whole age mapping to that thing. Where does age come in? Because now what you've done is you stored inside your brain the number 21. And it's just free floating there. You have no way of kind of running through your memory and saying, is this the 21 I'm looking for? Is this the 21 I'm looking for? Is this the 21 I'm looking for? We have to have a name value pair, way to match it. Go ahead. Sure. So we can do something like that. We can even do it in, we can do strings if we want. Most of the time, the examples we'll create are going to be name value pair like this. So we have a variable named A and a value is 21. We can call this age, certainly. So this is a name value pair. Makes enough sense, right? I have a to list. The car of that list is the variable name. The catter of that list is the variable value. All right. So now this allows me to have a single name value pair. How might we represent a bunch of name value pairs? What if I wanted to remember that age is 21 and well, let's just split to simple variables. Let's say I wanted to have A is 5, B is 7, C is 23. I have 3 different name value pairs. So A is 7, B is 5, C is 23, something like that. So I want to remember all these pieces of information. I need to have some sort of construct that will hold my name value pairs. What's that construct? What could I create based on what we know right now to hold my name value pairs? List of to lists. So I can put all this crap in a to list. I want to make it a little easier to read like this. So is that a list of to lists? Could we say that that is a variable environment? It is a collection of name value pairs. Fair enough? Okay. So maybe we say we're going to define our environment to be that guy. So we'll define a variable named env, and he's going to be equal to this list of to lists. All right. So now, when you, let's say that what we're looking at here is a visual definition of what's in your memory. And I say, what is the value of B? What do you have to do? When somebody asks you as a person to say what value is associated with B, you have to then go and resolve that variable name, right? So you go and do some subconscious stuff inside your head and you pull out the 5. So we need to be able to resolve a variable name. How would we resolve this? If I took that in as my variable environment and I wanted to say resolve B in my environment env. What if I wanted a function called resolve? And I took in the variable name that I want to resolve and then the place where it lives. And ultimately, I wanted this dude to spit out a 5 here. Similarly, if I said resolve D in env, maybe this guy boils down to a false, because D is not found in this memory. That makes sense? So we can go ahead and we can define resolve to be a lambda that takes in a var name and it takes in an environment, and it's going to look for that var name in that environment. So we'll have our cons. Our environment is a list, right? It's a list of to lists is the way we're creating it right now. So we're asking, is our environment empty? Have I looked everywhere? If I've looked everywhere, I didn't find it. We're done. If I still have places to look, how do I ask, is the variable that I'm looking at the car of my list equal to the thing I'm looking for? How do I ask the question if var name is equal to, in this case, age, is equal to the variable name at the car of this list? What's my conditional here for that? Go ahead. Okay. What will the car of ENV give me? What will this guy give me if this is my ENV right now? Yeah, the first two lists, this guy. But I want the first element of that guy, right? Because I want to compare var name specifically to age. So how do I get age out of that two list? Yeah, the car of the car, that dude. Or I could say the car of the car, if you like that better. Either one. Okay. So I'm asking the question, if the variable I'm searching for is equal to the variable name that's found in the first element of the list, I should then resolve to the value. So if this is true, how do I boil down to the value associated with that variable name? Well, the car of ENV, that gets me this two list, right? And I ultimately want to boil down to the 21. So how do I get a 21 out of that? Okay, I could take the car of the cutter. Well, actually, I'm going to write it in different things. So this is the car of that. I'm going to take the cutter of that. That's going to give me the list containing a 21. How do I get the 21? Take the car of that. The Kadar. Car of this list, give me this. Cutter of that list gives me that list. The car of that gets me the 21. So this is the car of the cutter of the car. The cutter.
So you, the car would give you
This guy.
that guy. You have to take the clear that and just like-
It would be the list containing the 21.
Oh, gotcha.
Yeah, cutter always returns a list. All right, so you could write it like that if you want the Kadar of ENV. I probably wouldn't go much deeper than that with the shortcuts. The car of the cutter of the car. I would say three letters is about as deep as you want to go before you start going a little loopy. Okay, so if I'm looking at the variable name that I'm interested in, boil down to its value. Else, I haven't found it yet. So I'm going to call resolve on the same var name I was searching for in the cutter of ENV. So now I should be able to say resolve B in ENV. I should be able to say resolve age in ENV. I should be able to say resolve D in ENV. There's my 5, there's my 21, there's my false. So now we have the ability to look up variables. Is this pattern really dissimilar to any of the things we've written so far? We just happen to be applying it to our imagined version of a variable environment. So this is how variables work. Just because. That's how I want to store them. We could have created a different structure. In fact, later on, we will create a little bit more complex structure because later on we'll be dealing with possible scopes where you could have two different variables named A. One is in a more, all variables boil down to the most local scope. So we might have a scope that gets put onto the front of the list temporarily while we're in the middle of a function running, something like that. All right, so there's our I think maybe the book where the I built the slides from, I think it might call this guy apply ENV. That guy there. I think the way I would usually refer to it is I'm resolving a variable in the environment. It means the same crap. Doesn't matter. Okay. So our first language. Here, I'll go ahead and I'll give us this inside of Scheme here. Or Slack here, rather. All right. So this entire thing we're looking at here is called a grammar. And each element of this is called a production. So what we're looking at here is our first mini programming language. This is the language that is a lambda calculus expression. All right, we always just throw the word calculus in there because it makes it sound scarier. All right, takes it from a 4 to like an 8. All right, so we have 3 different productions in our lambda calculus expressions. We have something that is just an identifier. We have something that is a lambda expression. And we have something that's a lambda calculus expression followed by a lambda calculus expression. What I want you to tell me is, from a programming language perspective, and based on what we've already been introduced to with Scheme, and this looks very much like Scheme, right? This is a dumbed down version of what we've seen in Scheme so far. One thing I'm pointing to here is this guy only supports exactly one identifier. I won't say more than that right now until after you've given me a better answer, but I can't have more than one identifier in the second production. So what I want you to tell me is, what problem is each of these productions solving? What programming language feature is each of these productions solving? Let's start off with this first one. If I had an expression, single line of code in my programming language that just was an identifier, like a B or a C, what problem is that solving? What kind of expression is that? Go ahead. Yeah, well, it's not a variable declaration, but probably a variable usage, a var expression. So if I just had the letter A sitting in the middle of my Java program, I expect that to get resolved to whatever A's value is. Make sense? So I'm going to come up here. We're going to say identifier is a variable expression. All right. What's this next one? What kind of animal does that second production mimic for us, represent for us? A function. So we kind of expect our programming languages to support functions, right? So a lambda, just like it is in Scheme, is an unnamed function. Presumably, since we also have something called an identifier, we maybe can map it to a name, right, by throwing a function into our variable environment. But in terms of the language definition right here, it sits on its own. We have a lambda, but this language, as it's defined right now, supports only functions with exactly one parameter. No more, no less. I can't have 0 parameter functions. I can't have 3 parameter functions. 1. Every function takes 1 input in my current definition of my language. I think we could probably assume that that's going to change, but in our first definition here, that's what it is. All right. So I can have a function that takes in a single input whose body, the body of that function, is some lambda calculus expression. Where right now our lambda calculus expressions are pretty simple. What's this last one? A list containing 2 lambda calculus expressions. What is that guy trying to solve? Go ahead. Nope. Yeah. Nope. Go ahead.
Expression is if we have an
No. We have to think about applying all this stuff. My first 2 productions here say, hey, I could have variable names that presumably will resolve down to a value. And oh, I can have functions that take exactly 1 parameter. So I ask you, how do I call my function? The last one. that last one. Here's seeing it in action. Let me give you a simple, we'll assume there's a variable environment here. Oh, I already have one, so let's just do this. So I'm going to create a list. In the first element of that list, I'll put a lambda x, and it'll just boil down to its value. I have a very simple programming language right now, right? I support functions that take exactly 1 parameter. Well, I don't have any mathy stuff I can do. This language definition just says, look, I can resolve variables. That's it. You give me a variable, I'll tell you the value it's associated with. That's all I can do in this language right now. So I can put that as my first parameter in the list. And the second one, I'm going to go ahead and we'll assume we've resolved our variable for that identifier. And that should give me a 5. So this guy right here should boil down to 5 being passed in to this function, which takes 5 as a parameter and just boils down to its value, which is 5. So this list here is an app expression. And if you like it better like this, I can just put a 5 in there like that. We'll say 5 is the value that my identifier resolved to. If we're looking at a var expression here, we have to say, what does this guy become? This guy's going to have to become the value associated with that variable name. So here's my, what I'm going to call an app expression. It's a list containing 2 lambda calculus expressions. Here's my first lambda calculus expression. It's my lambda production number 2. And here's my production number 1 resolved to its value. And that will give me that 5. So that last one is, how do I call a function passing it a parameter? Make sense? All right. Homework assignment is to do the sort from that previous slide. I'll put it up on Slack. We'll come back on Thursday and keep going here with our first language and writing an interpreter for it. What's up? Awesome. You excited? Oh yeah, extra credit homework is to watch The Hunt. Austin assigned it, so I have to approve it. I think I have. Yeah, I'm almost positive I've seen it. I don't recall it at all right now.